Today we're going to be giving a demonstration of testing an electrical installation with no supply connected. The very first test we're going to be performing is resistance of earthing conductors, and we're going to start with the resistance of the main earthing conductor. The purpose of the main earthing conductor is to provide a means where the electrical system, or all the earthing conductors on my electrical installation, are connected to the general mass of earth. Let's make a start. I perform a battery check, and then I'm going to test my tester. Zeroing out my meter. Connecting one end to the disconnected MEN link, and the other end I'm going to be connecting to the electrode. Not connecting it to the clip or the cable, ensuring I'm putting my probe onto the electrode itself. And an acceptable result is 0.5 ohm or less. It's worth mentioning here that if I'm reading a result of greater than 3 ohms on my meter, I might need to change my meter to the 500 ohm scale and test it again. Once I've finished, I test my tester. The second test we're going to be doing is the resistance of the equipotential bonding conductor. Now, examples of this might include pool fencing or a steel frame house, things like that. And the purpose of that equipotential bonding conductor is to ensure that all of these conductive parts are connected to the general mass of earth. Battery check, test my tester. Connecting one end to the disconnected MEN link, and the other end to my conductive parts. Again, testing to the pipe in this case, not the conductor itself, but the actual pipe. Looking for a result of 0.5 ohm or less. If my meter is reading 3 ohms or greater, again, I want to change my meter to the 500 ohm scale. Once I've finished, I test my tester once again for the correct operation. The next test we need to do is the resistance of the protective earthing conductors. Now, the purpose of this test is to ensure that under a fault condition, the resistance of those protective earthing conductors is low enough to permit operation of my protective devices within the required amount of time. If my resistance was too high, this circuit breaker would not trip in the required time. It would take too long for that circuit breaker to trip. So let's jump into it. A battery check. On the 3 ohm scale, I'm going to test my tester and zero that in. Connecting one end to my disconnected MEN link, and I'm testing each final sub-circuit on the very final point. So if I've got, say on circuit breaker 3, if I've got 5 power points, I go to the power point which is the furthest distance away, testing to the earth. And I need to be referring to table 8.2 to determine what is an acceptable result. So I need to record, firstly, is my resistance of the earth. Then I add the resistance of the earth to the predetermined phase resistance. And then I compare this to the RPHE reading on table 8.2. And so long as my calculated value is beneath the RPHE value on table 8.2, that complies. And test my tester. The next test we need to perform is insulation resistance. We'll start off with doing insulation resistance of the whole installation. Now the purpose of this test is to ensure integrity of the insulation between conductors of the consumer mains and submains, and integrity of the insulation between live and earth parts of an electrical installation. Step 1, disconnect the MEN link from the neutral bar. Step 2, we turn all circuit breakers on and all switches on. Next, we need to bridge the active conductors on the meter panel and next, we need to bridge the active and neutral terminals on the overhead mains box. I'm going to perform a battery check and testing my meter for correct operation. So on the 500 volt scale, I test my tester. Connecting one probe to the disconnected MEN link, and I can test to any active or neutral conductor in the installation. So I'm just going to test to my active conductor on the main switch, and I'm expecting a result of 1 mega ohm or greater. That's a pass. And testing my meter for correct operation. The next test we're going to be performing is insulation between the active and neutral on the consumer mains. Once again, my MEN link is disconnected from the neutral bar. I've turned my main switch off. I'm bridging the active conductors on the meter panel and testing my meter for correct operation. Battery check. On the 500 volt scale, testing my meter for correct operation. And test between the line side of the main switch here and the neutral bar. An acceptable result for that is 1 mega ohm or greater. And testing my meter for correct operation. The next test is insulation resistance of the consumer mains. Making sure my MEN link is disconnected from the neutral bar, the main switch is off, and again, bridging the active conductors on the meter panel. Test my meter, correct operation, a battery check, and on the 500 volt scale, testing my meter. Now I'm going to be testing between that disconnected MEN link and the line side of the main switch, looking for a result of 1 mega ohm or greater, testing between my disconnected MEN link and the neutral bar. Again, looking for the result of 1 mega ohms or greater, and testing my meter for correct operation. The final part of my insulation resistance testing is to be checking the final sub-circuit conductors. Once again, my MEN link is disconnected from the neutral bar. All of my circuit breakers are off, but I'm turning all of my switches on. Test the tester, the battery check, and 500 volt scale, testing my tester. Connecting one end to the disconnected MEN link and testing each final sub-circuit active and neutral conductors. So we really want to have a think about where we need to test within that switchboard. Are we testing on the line side of the circuit breakers or on the load side? Have a think about when the cables on the final sub-circuits enter the switchboard, where do they terminate to? That's where we need to test. So circuit 1 is a circuit breaker, so I'm going to test my active conductor there, looking for a result of 1 mega ohms or greater for each of these tests. Now my neutral in this case is going to be connecting to the neutral bar because of the circuit breaker. So I'm going to be testing to the neutral bar. A second circuit is an RCBO. So my active conductor is going to be connecting to the RCBO. Also, my neutral conductor is also going to be connecting to the RCBO. All of my tests there had a result of 1 mega ohms or greater once I've gone through and tested all of the circuits, test my meter for correct operation. And the test is done. Polarity testing is the next test that we need to do. We're going to start off with the polarity test of the consumer mains. Now the purpose of this test is to ensure there are no incorrect arrangements of conductors which could result in electric shock hazards. In other words, I'm making sure that my active conductor is terminating to where it should be, my neutral conductor is terminating to where it should be, and we're not crisscrossing any conductors. Let's make a start. As always, making sure my MEN link is disconnected from the neutral bar, turning all circuit breakers and switches off, and testing my meter for correct operation. Battery check, using the 3 ohm scale, testing my meter and zeroing in. I'm going to connect one probe to the active terminal on the overhead mains box. And the other probe is going to go to the first active conductor on the meter panel. An acceptable result there is a low ohms reading. Next step is connecting from my neutral terminal on my overhead mains box down to my neutral link on the meter panel. Once again, an acceptable result is a low ohms reading. Next thing I want to be testing is from my second active conductor on the meter panel to the line side of the main switch, looking for a low ohms reading. A low ohms reading is a pass. Testing from my neutral link on the meter panel to my neutral bar. Once again, an acceptable result is a low ohms reading. If I'm measuring a result of greater than 3 ohms on my meter, I want to be changing my meter to the 500 ohm scale and measuring again, because it's very possible I could be getting a result of perhaps 5, 10 ohms, and I'm not going to be able to measure that accurately on the 3 ohms scale. And finally, as always, testing my meter for correct operation. Next step is doing the polarity test operation of the main switch, making sure that all circuit breakers are off, testing my meter for correct operation, connecting one end of my tester to the second active conductor. And my other probe needs to go to the load side of the main switch. When I turn the main switch on, I would be expecting a low ohms reading. When I'm turning the main switch off, I would be expecting a high ohms reading. Once again, if I'm measuring a result of greater than 3 ohms, changing my meter to the 500 ohm scale. Once I'm satisfied with that, testing my meter for correct operation. And finally, polarity testing of the final subcircuits. We need to be testing operation of these switches. And again, active conductors are going to active terminals and neutral conductors are going to neutral terminals. And we're not crisscrossing anything. I'll connect one end of my meter to the protective device on the load side of the protective device, and the other end is going to be going on the final subcircuit at its final termination point and operating that switch. When the switch is on, I'd be expecting a low ohms reading, and when the switch is off, I'd be expecting a high ohms reading. Testing the neutral conductor of that final subcircuit. When the switch is on, I'd be expecting a low ohms reading. And when the switch is off, I'd also be expecting a low ohms reading. It's not very often that we switch a neutral conductor, so I'm not going to delve into that too deeply. You can speak to your teacher for a further explanation of that. I'd go through and test all of my final subcircuits, and each point and every switch. Once I've done that, testing my tester for correct operation. And we have now completed polarity testing. The next test that we need to perform is the earth fault loop resistance of the final subcircuit. The purpose of this test is to ensure that under a fault condition, the resistance of the active and earth conductors is low enough to permit operation of the protective device within the required time frame. In a nutshell, what that means is the whole loop, starting off at the active conductor, which goes down to my power point and returns via the earth from that power point up to the earth bar. That loop has to have a resistance low enough in order to permit that circuit breaker to trip in a quick manner. We need to make sure that resistance is low enough. So the very first step that we want to do is, as always, disconnect our MEN link from the neutral bar. We're turning off all circuit breakers and turning on all switches. Testing our meter for correct operation. And on the 3 ohm scale, I shall zero that in. And I want to place my bridge lead across both probes of my meter and zero my meter in with that bridge lead attached. Once I'm satisfied with that, bridging the active conductor of that circuit breaker to the earth bar via the disconnected MEN link, and with my probes from my meter, one in the active terminal, one in the earth terminal, and I'm measuring a result of 0.4 ohms there, and testing my tester. We need to be referring to table 8.2 to know if that's a pass or a fail, to verify that. And if I refer to table 8.2 for a 16 amp circuit breaker with a 2.5 millimeter cable, the RPHE value is 1.2 ohms. And I've measured about 0.4 ohms, therefore my test is a pass. I need to go through and repeat that for every single final sub-circuit. A couple of things we need to note. If you're measuring a value of greater than 3 ohms on your meter, you need to change the meter to the 500 ohm scale. The next test we need to do is to verify the RCDs. I've got 3 different RCDs here I need to verify. I've got a 10 milliamp, a 30 milliamp and a 100 milliamp RCD. For each of those RCDs, I need to be checking the trip time and the trip current. Total of 2 tests for all of those 3 RCDs. So if you like, there's 6 different tests across the 3 different RCDs. RCD 1, which is a 10 milliamp RCD. I changed my range here to 10 milliamp. I want to be checking the trip current, so I'm changing that to milliamps on the 10 milliamp setting and hit the test button. That's tripped at 8 milliamps. Good result. still on the 10 milliamp RCD, going to be testing seconds, milliseconds. So I'll press the button to change that to milliseconds, and I want to be hitting the test button to see how long that trips. 16 milliseconds, that's a good result. From here, we just need to repeat the process for all of those 3 RCDs. Changing that to 30 milliamps, changing that to the milliamp setting. I want to be testing my leakage current. I hit my test button. That's tripped at 27 milliamps. Good result. This time, changing that to milliseconds, testing how long that takes to trip. 9 milliseconds, that's a good result. Finally, let's test the 100 milliamp RCD. Changing that to 100 milliamps, putting it on the milliamp setting, hitting the test button. That's tripped at 80 milliamps, good result. Changing the range to milliseconds. And let's test that. Tripped in 9 milliseconds. So there we have it. We've now completed testing our RCDs. Next test we need to do is be testing our appliance. 2 things. We need to be testing the earth continuity of that appliance and the insulation resistance. I'm going to start off with the earth continuity. First thing I need to do is to be checking my meter, do a battery check. And on the 3 ohm scale, I'm going to 0 that in. Okay, that's pretty good. Connecting one of my probes to the earth pin of my plug. And the other probe, I'm going to test the frame of the appliance. I'm going to do this in 3 different spots just to make sure I'm getting a good reading. I'm measuring about 0.3 ohms there, which is a pass. .3, 0.3. So we need to be picking a metallic part of the appliance frame, something that's conductive. An acceptable result is half an ohm or less, so that's a pass. The next test I need to be doing is insulation resistance. As always, I need to be testing my tester. On the 500 volt scale, I'll test my tester. That's working good. Connecting one end of the probe to the earth pin. Now before I proceed, I need to be turning this appliance on. I need to be turning it to its highest setting, and if there's an on button or a lever or something you have to turn on, you have to turn it on too. For instance, the toaster. So I'm cranking this one right up to its highest setting. That's on high. If this was a toaster, I'd be turning it on too. Testing from the earth pin to the active. From the earth pin to the neutral. And acceptable result is 1 mega ohms or greater. Now that would be for a non-sheafed element. So an appliance containing a non-sheafed element would be a result of 1 mega ohms or greater. If the appliance contains a sheafed element, the acceptable result would be 0.01 mega ohms or greater. And testing my tester. Now I think it's important, I'll just turn that off. we point out the difference between a sheathed element and a non-sheathed element. A sheathed element is what you might find in a hot water service or one of the old-fashioned stove tops. For instance, with a stove top, one of the old-fashioned ones, if you touch it, you're going to get burnt, but you won't get electrocuted because there's a coating on the element which prevents you from getting electrocuted. You just get burned. A non-sheathed element, if you touch a non-sheathed element, you're going to get electrocuted. So that's the difference between a sheathed element and a non-sheathed element. And that concludes the appliance testing.